All right, welcome to another deep dive where we take your suggestions for sources and sort of extract, well, the key insights that are going to be valuable to you.
That's right.
And for this deep dive, our listener is, well, a philosopher.
Oh, interesting.
Yeah, someone who's deeply immersed in, well, the foundations of knowledge
Yeah.
and reasoning.
Yeah.
And they've sent us toward this pretty fascinating area, intuitionism.
Okay.
Specifically in philosophy of mathematics, using, well, the Stanford Encyclopedia of Philosophy.
That's a great resource.
Yeah, it's a really comprehensive entry.
It is.
So, philosopher listener, get ready. Our mission is to unpack this whole thing.
Yeah.
All these core tenets of intuitionism, what it means for math, for logic,
Right.
and even like how it connects to these bigger philosophical ideas.
Yeah. The implications are pretty profound.
Yeah, and we're going to do it without, getting bogged down in the weeds.
Exactly.
We want to surface the most intriguing stuff for you.
The really juicy bits.
Yeah, the good stuff.
Yeah. So we're offering you a focused exploration of this alternative way of thinking about mathematics. We really want to highlight where it aligns with traditional philosophical viewpoints, but
Really?
also where it clashes.
Okay, so let's get into it.
Let's dive in.
Intuitionism, at its core, it kind of comes from this Dutch mathematician, L.E.J. Brouwer, early to mid 20th century guy.
Yeah.
Now, for our listener, a philosopher, deeply concerned with epistemology. This is where it gets interesting.
Definitely.
Brouwer says math is a creation of the mind.
Yeah.
So does that mean that mathematical truths are, like, fundamentally different
That's a huge question.
from empirical truths
That's it.
about the world?
That's the key starting point for intuitionism.
Right.
Brouwer's central tenet is this.
Yeah.
Math is not some external reality, right?
Right.
It's not like a platonic realm of forms
Yeah.
waiting to be discovered.
So it's not like we're searching for something out there.
No, it's not like
Okay.
that. Instead, for an intuitionist, mathematical truth happens when we construct a mental proof.
Okay.
Like we, as thinking subjects, we build it.
So it's not about discovery. It's about creation.
Exactly.
Okay.
And communication between mathematicians. It's not about sharing discoveries. It's about guiding others to do the same mental constructions.
So it's very active, very constructivist.
Very much so, yeah.
Putting the knowing subject
Right at the center.
at the center of
Yeah.
mathematical truth.
Exactly.
Okay, so Brouwer's journey to this philosophy.
It's pretty fascinating.
Yeah, tell me more.
He was a well-respected mathematician, especially known for his work in topology.
Like groundbreaking work.
Yeah, groundbreaking stuff.
Okay.
But around 1913, he kind of shifts his focus. He starts looking at the philosophical foundations of mathematics.
Okay.
This was during a time of intense debate,
Okay.
the Grundlagenstreit.
Oh, wow, big word.
Yeah, it's a mouthful.
What was that about?
Basically, mathematicians and philosophers were freaking out
Okay.
over paradoxes and non-constructive proofs. They were looking for solid ground, like a secure foundation for math.
So more secure epistemologically.
Yes.
Ontologically.
Absolutely.
Okay.
So intuitionism was Brouwer's answer to this crisis.
Like his way of grounding mathematical knowledge in something more immediate and certain.
Yeah, he wanted a foundation and the direct experience of the thinking subject.
Okay, I see.
And there's this interesting tidbit, even before he went full on into philosophy of mathematics, his 1905 book,
Okay.
Life, Art, and Mysticism, kind of hinted at his later solipsistic ideas,
Okay.
suggesting that math is deeply rooted in individual experience.
So very internal.
Very internal.
Okay.
And, his ideas were controversial.
Mm-hmm.
He clashed with people, especially Hilbert.
Yeah, I can imagine.
But he also got respect from big names like Gödel and Wheel.
Okay, so he was taken seriously.
Oh, absolutely. He shook things up.
All right, now the article mentions these two acts of intuitionism.
Yes.
Sounds kind of fundamental
Oh, very
to his
fundamental.
whole philosophy.
It is.
Can you walk us through those, keeping in mind our listener,
Yeah.
their interest in foundational principles?
Absolutely. So the first act is all about separation.
Separation.
Yeah, you completely disconnect intuitionistic mathematics from formal language
Okay.
and theoretical logic.
Interesting.
It's a radical move.
So you're saying math doesn't need language or logic to exist.
For Brouwer, that's exactly it.
Okay, so how does that work?
He saw intuitionistic mathematics as this languageless activity that comes from our perception of time.
Perception of time. Now, this is where it gets really interesting.
This is the core of it.
Yeah, how does this basic experience lead to something as abstract as mathematics?
Brouwer described it as this. A single moment of life splits into two things,
Okay.
the past and the present.
Right.
But Importantly, the past is retained in memory.
So we hold on to it.
We do this basic separation. This two-ness, stripped of any specific content, becomes the empty form.
The empty form.
The underlying structure of all mathematical thought.
Okay.
That, for Brouwer, is the primordial intuition of mathematics.
So awareness of succession of before and after,
Yes.
that's the seed of all mathematical concepts.
Precisely.
It's like math is born directly from subjective experience.
That's the core of the intuitionistic view.
Oh, okay.
And from this first act, you get the natural numbers.
Okay.
One, then another, and so on.
Just by repeating this act of distinguishing and remembering.
Exactly.
Okay, so what's the catch?
Well, this first act also puts a limit on how we reason.
Okay.
We have to reject the principle of the excluded middle.
PE, right? The idea that any proposition has to be true or false.
Exactly. A or not A.
Right. A or not A.
But for an intuitionist, that's only valid if we have a constructive proof.
Okay.
Either of A or of not A.
So if we don't have a proof either way,
then PEM doesn't hold.
Interesting.
Now, some people might worry that this makes intuitionistic mathematics kind of weak.
Yeah, like it's missing this fundamental logical tool.
Right.
But that's where the second act comes in.
Exactly.
It's meant to compensate for that, right?
It is.
To give us a richer mathematical landscape within these constructive boundaries.
Exactly.
All right, so tell me about the second act.
The second act introduces two ways of creating new mathematical entities.
Okay.
First, you have infinite sequences. These are sequences of previously established mathematical entities.
Okay.
But they're created more or less freely.
So, like, I pick a number, then another, and so on.
Exactly.
And I don't have to follow a specific rule.
You got it.
Okay. And what's the second way?
The second way is through mathematical species.
Mathematical species? What are those?
Essentially, they're properties that can be applied to mathematical entities.
Okay.
But with a key condition. If a property holds for one entity, it has to hold for anything equal to it.
So, like, if one number is even and another number is equal to it,
then the second number also has to be even.
Okay, I see.
That makes sense, right?
It does.
It preserves equality.
Right.
So this second act, especially the idea of freely proceeding sequences, helps us build more complex mathematical objects.
Okay. Like what?
Like the continuum.
Ah, the continuum.
Yeah, it's a big one.
Absolutely. It's central to analysis.
Exactly.
So how do these freely proceeding sequences get us to the continuum?
The key is choice sequences.
Choice sequences.
These come from that first way of creating new entities.
Okay, the infinite sequences.
Yes, the ones we build freely.
Okay.
These sequences, where each term is chosen without a fixed rule, they're the foundation of the intuitionistic continuum.
So we're not assuming some pre-existing continuum out there.
No, not at all.
Like Platonism might suggest.
Right. This is very different from Platonism.
Okay.
And it's also different from formalism.
Which sees math as just symbol manipulation.
Exactly. Intuitionism is all about construction.
We build mathematical objects.
Yes, either mentally or through a clear procedure.
Okay, I see.
So this freedom in constructing infinite sequences, that's what sets intuitionism apart from other constructivist views in math.
Okay, so it's not just about being constructive, it's about this specific kind of construction.
Exactly. It's about choice sequences and the freedom they bring.
Okay, and that freedom leads to some pretty big deviations from classical mathematics, right?
Oh yeah, huge deviations.
We talked about the rejection of PM.
Right, that's a major one.
What are some other key differences our philosopher listeners should know about?
Another big difference is time dependence of truth.
Okay, time dependence, what do you mean?
In intuitionism, a statement's validity can change over time.
Really?
Yeah, it's not fixed eternally.
So it's not like a Platonic truth that's always true?
No, not at all.
Okay.
It becomes true when we find a constructive proof.
So mathematical truth is dynamic.
It is. It evolves as we make new constructions and proofs.
That's a very different picture of mathematical reality.
For sure.
Than what most philosophers might be used to.
Yeah, it's a big shift.
Okay, and then there's the continuum.
Right, the continuum.
We touched on it with choice sequences, but how is the intuitionistic continuum different from the classical one?
It's not just a smaller version.
Okay.
It's fundamentally different.
In what way?
It has properties that the classical continuum doesn't.
Give me an example.
For instance, in intuitionism, all total functions on the continuum are continuous.
Whoa, wait a minute.
Yeah, it's a big one.
In classical analysis, there are definitely functions that are defined everywhere, but not continuous.
Right, but those don't exist in intuitionistic mathematics.
So how does intuitionism rule those out?
Well, the classical counterexample.
Like the function that's 0 for rational numbers and
Yeah.
1 for irrationals,
Exactly.
that's not continuous anywhere.
Right, but in intuitionism, we can't even define that function
Why not?
because we can't decide whether a given real number is rational or irrational.
We don't have a constructive way to do that.
Exactly.
So that discontinuity just doesn't arise in the intuitionistic framework?
It doesn't.
Okay, that's wild.
It is.
Now, the article mentioned this thing called the creating subject,
Yes.
which sounds a little strange.
It can be a bit tricky.
Yeah, especially for a philosopher who's thinking about objectivity.
Right.
So what is the role of this creating subject in Brouwer's intuitionism?
So the creating subject addresses a couple of concerns.
Okay.
First, it avoids a purely psychological interpretation.
Where math would be totally subjective?
Yeah, varying from person to person.
Right.
The second concern is intersubjectivity.
Okay, how different mathematicians can agree on mathematical truths.
Exactly.
So how does the creating subject solve these problems?
It's basically an idealized mind.
An idealized mind.
Yeah, like a perfect mathematician.
Okay.
It's timeless, it has no limitations,
No memory constraints, no errors in reasoning.
none of that.
Okay.
And all intuitionistic mathematics takes place in this mind.
So all mathematicians are tapping into this one mind.
That's the idea.
So it's like a universal mathematician
In a way, yes.
that kind of sidesteps the issue of individual subjectivity.
It does.
Okay. And how did Brouwer use this creating subject?
He used it to construct strong counterexamples.
Strong counterexamples.
These go beyond just saying something's unproven.
Okay.
They aim to show that certain classical ideas are actually false.
False.
Yeah, within intuitionism.
Okay, that's pretty strong.
It is.
And what about Kripke's schema?
KS.
Yeah, KS. The article mentioned it.
Yeah, KS is often justified using the creating subject.
Okay.
It links the truth of a statement to a specific kind of choice sequence.
Okay, I see.
But, interestingly,
Yeah.
the creating subject itself hasn't had as much impact on the day-to-day development of intuitionistic mathematics.
Really?
Yeah, the two acts are much more influential.
Okay, so the creating subject is more of a philosophical justification.
Yes, it helps us understand the foundations,
Mm-hmm.
but the two acts tell us how to actually do math.
Okay, I get it.
It's like the difference between the blueprint and the actual building.
All right, let's move on to intuitionistic logic.
Okay, IQC.
IQC, right? So intuitionism has a different view of truth.
Right.
So it makes sense that its logic would also be different.
Exactly.
How does it depart from classical logic?
Well, as we've seen, the BHK interpretation is key.
Brouwer hating Kolmogorov interpretation.
Yeah, that's the one.
Okay.
And instead of defining logical connectives by truth values,
True or false?
right,
Yep.
BHK defines them by proofs and constructions.
Okay, so how does that work?
For example, a proof of A and B
Mm-hmm.
means you have a proof of A and a proof of B.
Okay.
A proof of A or B
Yeah.
means you have either a proof of A or a proof of B,
Okay.
and you know which one you have.
Makes sense.
A proof of A implies B
Mm-hmm.
is a method to transform any proof of A into a proof of B.
So it's about transformation, not just truth values.
Exactly.
Okay. And what about quantifiers?
For all x, P of x, a proof is a method that works for any possible x. If there exists an x such that P of x,
Mm-hmm.
you need a specific x
Yeah.
and a proof that P holds for that x.
So it's all about actually having the thing, not just saying it exists.
That's the heart of it.
And is it this shift in meaning
Mm-hmm.
that forces us to reject PEM in IQC?
Exactly.
Okay.
Because to prove A or not A,
Yeah.
we need either a proof of A
Okay.
or a proof that A is impossible.
Right. And if we don't have...
That A or not A is not provable.
So it's not universally valid.
Exactly.
Okay. So who formalized this intuitionistic logic?
Hating.
Hating. Okay.
He formulated the first complete system,
And what's it called?
intuitionistic quantifier logic, or IQC.
IQC. All
It's
right.
basically classical logic without PEM.
So are there any other key features of IQC?
Yeah, one is the disjunction property.
DP.
Yeah, DP.
Okay. What's that about?
It says that if IQC proves A or B,
Mm-hmm.
then IQC must prove A or IQC must prove B. Classical logic doesn't have that.
Right. Classical logic can prove A or not A, even if we don't have a proof for either.
Exactly.
Interesting.
There's also some debate about ex falso sequitur quod libet.
What's that?
It's the principle that from a contradiction, anything follows.
Okay.
It's usually included in IQC, but there's debate about whether Brouwer fully accepted it.
Okay, so IQC has this strong proof is meaning flavor.
It does.
Very constructive.
Very much so.
Okay, and what about the theoretical side of things?
Well, IQC is very well behaved theoretically.
Oh,
There are sound and complete proof systems for it,
like what?
like Gensen calculi and natural deduction,
Mm-hmm.
and it has a rich model theory.
With things like Kripke models and Beth models?
Exactly.
Okay.
These models are often defined classically,
Okay.
but they're still valuable tools for understanding IQC.
Okay, so we can use classical tools to study intuitionistic logic.
We can,
Interesting.
and then there's the Curry-Howard isomorphism.
Okay.
It connects proofs in IQC to computations in lambda calculus.
So it shows this deep link between proof and computation.
Yeah, it highlights the computational nature of intuitionistic logic.
Okay, so let's talk about the natural numbers.
Okay.
Brouwer's first act ties them to the perception of time.
Right.
So how does that affect how intuitionists understand the natural numbers?
Well, they still arise from that first act.
The separation of a moment into past and present?
Exactly.
Okay.
But the key difference is that infinity is always potential.
Okay, so the natural numbers are potentially infinite.
Yes, but we never grasp them as a completed totality.
So we can't just assume that every statement about all natural numbers is meaningful.
Right. We need to be careful about quantifying over the whole set.
But basic arithmetic still works,
Yeah.
right?
Yeah.
Addition, multiplication, induction.
Induction is fine.
Okay.
And for a lot of basic finite statements,
Mm-hmm.
intuitionism and classical math actually agree.
Like what?
Like prime factorization,
Okay.
or the existence of non-computably enumerable sets, and even PEM holds for quantifier-free statements.
Okay, so for things that don't involve infinity, we're mostly on the same page.
Pretty much.
But when we get to more complex theorems...
Especially ones involving infinity.
Right.
The intuitionistic proofs can get really hairy.
Okay, so that's where the real differences start to show up.
Yeah, when we move beyond the finite.
Now, you mentioned weak counterexamples and choice sequences.
Yeah.
Let's unpack those for our listener.
Okay, so weak counterexamples are Brouwer's way of showing that intuitionism matters.
Matters.
Yeah, that it changes what we can prove.
Okay.
They show that certain classical statements...
Statements that are true in classical math
Yes.
are not provable intuitionistically.
Give me an example.
Okay, let's take Goldbach's conjecture.
Every even number greater than 2 is the sum of 2 primes.
That's the one.
Okay.
Now, we don't know if that's true or false,
Right.
but we can define a sequence of real numbers called Rn,
Mm-hmm.
where if Goldbach's conjecture is true, Rn is always 0. Okay.
And if it's false, Rn becomes non-zero at some point.
Okay, I see.
Now, let's say R is the limit of this sequence.
Mm-hmm.
We can't say whether R is 0 or not.
Because we don't know if Goldbach's conjecture is true.
Exactly.
So we can't say R equals 0 or R is not equal to 0.
Right.
And that means the law of trichotomy doesn't hold.
For this specific R, yes.
Okay, so this is a weak counterexample.
It is.
It shows that we can't just assume a statement or its negation must be true.
Precisely.
Okay, but there's a difference between not being true and being refutable.
Right. Big difference.
Okay, what's the distinction?
Not being true just means we don't have a constructive proof.
Okay.
But being refutable means we have a proof of the negation.
Okay, so in this case.
We don't have a proof that R equals 0 or R is not equal to 0.
But we also don't have a proof that the law of trichotomy is false.
Right. It's a subtle point.
Okay, I see.
And it turns out that the full negation of the law of trichotomy is actually refutable in intuitionism. Yeah, because of the continuity axioms.
Wait, now we're getting to choice sequences and continuity axioms.
The heart of the intuitionistic continuum.
Yeah, explain this to me.
All right, so choice sequences. They come from Brouwer's second act.
Okay.
They're infinite sequences where each term is freely chosen.
Okay.
These choices can be based on a rule,
Okay.
in which case the sequence is law-like,
Law-like. Okay.
or they can be made without a rule.
So, random.
Kind of, yeah. Then the sequence is lawless.
Lawless.
A classic example is an infinite series of coin flips.
Each flip is not determined by the previous ones.
Exactly.
Okay. And why are choice sequences so important?
Because for intuitionists, all infinity is potential.
Okay.
So infinite objects have to be constructed step by step,
Mm-hmm.
and choice sequences are how we do that.
Okay. I see.
And Brouwer had this radical idea.
Okay.
He said every real number is represented by a choice sequence.
Wow. Okay, so that's a big departure from the classical view. And these choice sequences, especially the lawless ones,
Yes.
they justify the continuity axioms?
Exactly.
Okay, tell me about the continuity axiom.
The weak continuity axiom, WGCN,
WCN.
it says that if we have a property
Mm-hmm.
that holds for every choice sequence,
Okay.
then the point at which that property holds has to be determined by a finite initial segment of the sequence.
So we can't depend on the entire infinite sequence.
Right, because we only ever know a finite part of it.
Especially for lawless sequences.
Exactly.
Okay, that makes sense.
And then there's the full continuity axiom.
CN.
Right, CNN.
Okay, what does that say?
It says that the relationship between the initial segment and the point where the property holds can be expressed by a continuous functional.
Okay. So it's not just that it depends on a finite segment,
Right.
it's that it depends on it continuously.
Exactly.
Okay, and what are the consequences of these axioms?
They have some pretty big consequences.
Like what?
For example, CN implies that the universal PEM is false.
The one that says for all alpha, P of alpha, or not P of alpha.
That's the one.
Okay.
And it also implies that every total function on the continuum is continuous.
Wow, that's a huge difference from classical math.
It is.
So the intuitionistic continuum is way smoother than the classical one.
Much smoother.
Okay, and what about the bar theorem and the fan theorem?
Those are important too.
How do they fit in?
Well, choice sequences and continuity axioms, they're not enough to recover all of the classical analysis that Brouwer accepted.
Okay.
Like the theorem that every continuous function on a closed interval is uniformly continuous.
Okay.
That's where the bar theorem comes in.
Okay, what's that?
The principle of induction over well-founded trees.
Okay.
But Brouwer's justification for it was a bit shaky.
So there's some controversy there.
Yeah, but the fan theorem, which follows from the bar theorem, is more widely accepted.
Okay.
And it's crucial for proving things like uniform continuity.
Okay, what does the fan theorem say?
It's a form of compactness for fans. These are special kinds of spreads.
Spreads, those are like intuitionistic sets.
Yeah, sort of.
Okay.
And a fan is a spread where there are only finitely many choices at each step.
Okay, I see.
The fan theorem says that if a property holds for every infinite path through a fan, then there's a finite level where it holds for all paths beyond that level.
Okay.
It's like a constructive version of Koenig's lemma.
Okay, so it's a way to reason about properties that hold uniformly across infinite structures.
Exactly.
And Brouwer justified this using his bar principle.
Yeah, the one for the universal spread.
Okay, so it all ties together.
It does.
All right, what about the axiom of choice?
That's a tricky one.
Yeah, how does it fare in intuitionism?
The full axiom of choice.
The one from set theory.
Yeah, that one.
How-
It's generally considered unacceptable.
Okay, why is that?
Because it lets you assert the existence of things without actually constructing them.
Okay.
Like choosing an element from each set in a collection, even if you don't have a rule for how to do it.
So it's not constructive enough.
Exactly.
But there are weaker forms, right?
Yes, like the axiom of countable choice.
ACN.
Right, ACN.
Okay.
That one's okay because you can make the choices step by step.
So it's still constructive?
It is.
Okay, and what about the axiom of dependent choice?
DCN.
Yeah, DCN.
That one's also considered justifiable.
Okay, so intuitionism is really picky about what it accepts as a valid proof.
It is. It's all about constructivity.
All right, so we've seen how intuitionism affects different areas of math.
Yeah, from logic to analysis.
Now let's talk about its meta-mathematics.
Okay.
How has it been formalized, and what can we say about its properties?
Well, Brouwer himself wasn't too keen on formalization.
Right, he saw math as an internal activity.
Exactly.
But others came along and did it anyway.
They did.
Okay, so what happened?
Hating formalized intuitionistic arithmetic.
Okay.
It's called hating arithmetic, or HA.
HA. All right.
It uses the same axioms as Peano arithmetic, PA,
Okay.
but it's based on IQC instead of classical logic.
So same axioms, different logic.
Exactly.
And what's special about HA?
It has some cool properties,
Okay.
like the disjunction property.
DP.
Yeah, DP,
Okay.
and the numerical existence property.
NEP.
Right, NEP.
Okay, what do those say?
DP says that if HA proves A or B, then HA proves either A or B.
Okay.
NEP says that if HA proves there exists an X such that P of X,
Yeah.
then there's a specific